Hello everyone, welcome to our project demonstration. Today, we are going to present and study a forced oscillator, a system that vibrates under the influence of an external periodic force. Our aim is to construct a simple forced oscillator circuit using basic electronic components and study its response to an external driving signal. Hello everyone, welcome to our project demonstration. Today, we are going to present and study a forced oscillator, a system that vibrates under the influence of an external periodic force. Our aim is to construct a simple forced oscillator circuit using basic electronic components and study its response to an external driving signal. In physics, an oscillator is a system that repeats its motion in time, like a pendulum or a mass on a spring. When an external periodic force is applied to it, we call it a forced oscillator. The general equation of motion is ma dot x plus k dot x plus cax f0 ra sin omega t. Here, m is the mass, c the damping coefficient, k the stiffness, and f0 sin ot is the external driving force. The system's response depends on the frequency of this driving force, a key phenomenon known as resonance. For this electronic version of a forced oscillator, we have used one NPN transistor, BC547, one 10 kilo-ohm resistor, an LDR or light-dependent resistor, an LED as the output indicator, a 9-volt battery for power supply, and a breadboard for the connections. The transistor and LDR together form a light-controlled amplifier, which responds to external periodic light signals. Let's understand how this circuit works. The LDR and resistor form a voltage divider that controls the base voltage of the transistor. When light intensity increases, the LDR's resistance decreases, increasing the base current, which switches the transistor on, lighting up the LED. When light decreases, the transistor turns off and the LED goes out. Now, if we shine a periodically blinking light, such as a mobile flashlight strobe, on the LDR, the transistor and LED begin to respond periodically to that light signal, just like a mechanical oscillator responding to a periodic force. In this way, the external light acts as the driving force, and the transistor-LED combination acts as the driven oscillator. Now, let's demonstrate the forced oscillation effect. I'm using a mobile flashlight app that blinks at different frequencies. First, let's set it to 1 Hz. That means 1 blink per second. As you can see, the LED turns on and off, exactly in sync with the blinking light. The circuit follows the external forcing frequency. Now let's increase the frequency to 5 Hz. The LED still responds, but with a small delay. The system is beginning to lag behind the forcing signal. Finally, at around 10 Hz, the LED no longer follows each blink distinctly. It appears dim or continuously glowing. This behavior shows that our circuit, like any forced oscillator, has a limited frequency response range, beyond which it cannot keep up with the forcing frequency. We can summarize our observations as follows. At low forcing frequencies, the system response is strong and in phase. As the frequency increases, the amplitude of response decreases, and the phase lag increases. This is analogous to a damped mechanical oscillator, where amplitude varies with driving frequency, showing a clear resonance behavior. To conclude, we successfully built a simple forced oscillator circuit using an LDR and a transistor. By changing the frequency of the external light source, we observed how the system's response varies, demonstrating the fundamental characteristics of forced oscillations. This experiment not only helps us understand the physics behind resonance and damping, but also shows how these concepts apply to real-world electrical systems. We thank our Department of Basic Science and Humanities at the Institute of Engineering and Management, Kolkata, for their guidance and support. Thank you for watching.